Okay, so to get started to talk about elementary matrices, when's the midterm? Probably sometime in November. We still haven't gone through all the material yet for the midterm, so I would like to do that first before kind of thinking about a midterm. So to start talking about elementary matrices, I really want to talk about seeing viewing matrices as a you can think of it as a function that acts on the elements in a matrix. So if I want to think of the matrix ABCD times the matrix XYZW, I really want to see what is this matrix doing ABCD to the elements of XYZW. So we have our formula for what that does. It's X plus BZ, etc. So, but what I want to try to think about is, can we express the rows of the product as a linear combination of rows of the matrix? So this is what I mean. So look at the first row of the product, AX plus BZ and AY plus BW. Can you write that as some linear combination of the rows of the second matrix? Can someone see what they would be? What is this alpha and beta? Just A and B, yeah. So if you think about it as splitting up this row, the A element is has X and Y multiplied. So I can think of this as A X times XY and then plus B ZW. So this gives a nice kind of representation of what the row in the product as A times the first row plus B times the second row. So so while we're here, can someone say what the third row would be? How can you express CX plus DZ as a linear combination and CY plus DW? What would that be as a linear combination of the rows? Good, yeah, C row, well, there's no row 3, but I think you mean row 1 and row 2. It would be C times XY plus D times ZW, which is C row 1 plus D row 2. So if you think about it a little bit, what you really could do is you can view matrix multiplication and kind of shrink down your second matrix into a column of rows. So I'm viewing this as a column of row vectors. Now, if you do the matrix multiplication, you get A row 1 plus B row 2 and C row 1 plus D row 2. Does that make sense? In fact, that could be kind of a easier way to look at matrix multiplication. You know, instead of looking at these 8 elements with this formula, you can think of it, kind of simplify it to down like this. So does everyone see that expression? Expressing the matrix multiplication as the multiplication of rows. All right, great. So that's pretty nice. And that should look kind of like suspicious. So we have A row 1 plus B row 2, C row 1 plus D row 2. All right, so when thinking about elementary matrices, let's ask this. What should A, B, C, D be to get row operations? So that question makes sense. So remember what our row operations were. I'll leave that to your discretion. Maybe ask me that after class or something. So what do I mean by that? So can someone remind me what our type 1 operations are? Our type 1 row operations. So now we're going back to Gaussian elimination. What was row 1 operation or type 1 operations? Remember, this was the row swap, right? So you swap 2 rows. Let's just start easy. Row 1, swap row 2. All right, so if I want to swap row 1 and row 2 in the second matrix here, what should A, B, C, D be to do that? So essentially what I'm asking is, if I have A, B, C, D times row 1, row 2, and I want it to be row 2, row 1, what should A, B, C, D be? This is just algebra. Does the question make sense? So what is it? Yeah, if A is equal to 0 and B is equal to 1, then what's left? What's left is just row 2 in the first row. If C is equal to 1 and D is equal to 0, what's left is just row 1. So if I do 0, 1, 1, 0, this matrix looks familiar, right? Times row 1, row 2, I get row 2, row 1. So let's just see if that makes sense if you're putting it in normal matrix form instead of this row of column of rows thing. All right, let's do the matrix multiplication. All right, what goes in the first entry here? So we're doing the matrix multiplication now. So what goes in the 1, 1 entry? 0x plus 1z, good. So z. And then what goes in the 1, 2 entry? W. And then the 2, 1 entry? X and Y. So good. So this matrix here is the row 1 swap row 2 operation. So what we're doing here is we can express row operations as some result of matrix multiplication. And later we'll see why that's very, very important. But does everyone understand so far, what's going on here? Does that make sense? Do you see why that matrix is the row swap operation. Okay, cool. All right, let's do the other ones. All right, we have let's do A, B, C, D. And I want to make it into alpha row 1 and row 2. So this is a type 2 operation. Right, this one was multiply a row by a constant. All right, so what do you think it should be? What's our A, B, C, D? So we're solving for A, B, C, D here. So if you don't like alpha, just put a 2 there for now or something. Yeah, if you don't have the homework in now, you can hand it in later, that's fine. All right, so we're solving for A, B, C, D. So we want these to be equal. C equals, well, so if C equals 1, oh yeah, C equals 0, right? Because that gets rid of the R1. We don't want that. D equals 1. I agree with that. That's good. And B equals 0 is good. So, and what would A be? A would be alpha. Not 1, right? 1 would just make it nothing, right? No change. So A is the constant of multiplication. B is 0, C is 1, sorry, C is 0 and D is 1. So if you want to look at that as a matrix, we have alpha 0, 0, 1. So this is the matrix that multiplies a row by a constant, in particular row 1. Yeah, we can resubmit homework. Okay, let's just double check. What's the first row? Sure, yeah, alpha x. And then what's the second element of the row? Or this entry here? Alpha y, yeah. And then what's this entry here? C. And this entry, W. Yeah, notice that alpha is only affecting the first row, right? When you do matrix multiplication, entries in the first column of the left matrix only affect the first row in the second matrix. So good. Can someone guess what, or not guess, but figure out, what would it be to make a multiplication in the second row? So where would the position of alpha be? How does it differ from alpha times the first row? Yeah, so what in the second row? Yeah, in the second row, replace that one with alpha. And does the first row change? Yeah, so it's going to be 1. Good. So good, those are the type 2 operations. So alpha 0, 0, 1 and 0, or not 0, 1, 0, 0 alpha are the type 2 operations. Again, this is for 2 by 2. We'll figure out, try to think about what 3 by 3 would look like. So it's alpha row 1. So we might have written this as row 1 to alpha row 1, or row 2 to alpha row 2. Okay, so any questions on that one? All right, so now let's do type 3. So type 3, so this was, we used type 3 a lot in Gaussian elimination. So this is when you you added a multiple of another row. It's a bit more involved here. So can someone try to figure it out? So maybe we can write out 1, yeah, like that. So there's 1, 0, and then alpha 1. Oh, can't see them. I might need to sign in. Just give me a second. It should be. All right, it's not, I guess, not up saving right now. So at the end of class, I'll figure that out. Oh, it did work. Great. Cool. Okay, so yeah, so this works. So if you put alpha, you said 1, 0, 1, 1, but this would need to be an alpha, right? That is what you're affecting row 1 by. This tells you add a multiple of row 1, an alpha multiple of row 1. So, yep, I have row 1 plus 0 row 2, and I have alpha row 1 plus row 2. Okay, so just to double check. Does everyone see that, by the way, as I'm writing this out? So that is x, y, and then alpha x plus z, and alpha y plus w, which is the row operation. So right, this is the row 1 part, or alpha row 1 part, and this is the row 2 part. Okay, cool. Any questions on that one? All right, and what do you think the similar operation would be for doing like row 1 plus alpha row 2? So this was used mostly in Gauss-Jordan elimination, putting things into reduced row echelon form. What do you think? Where would the position of alpha be? One alpha, yeah, 0, 1. Good. So those are type 3 operations. are type 3. So that's pretty significant because let's think about when we did reduced row echelon form for 3x3s. Can someone recall what are the kind of all the possible, what were some common reduced row echelon forms for 3x3? So first of all, what must be true in reduced row echelon form for 3x3? Give me some of the entries. There are some entries that you should know for reduced row echelon form. So how does reduced row echelon form look? There's ones and zeros somewhere. I agree with the one, but there might be entries here, right? Yeah, there's one at the 1, 1. Yeah, there are definitely these leading zeros. So big question. So sometimes if there's all ones here, what can you do if all the diagonal elements are 1? How can you, what would the rest of the reduced row echelon form look like? The above would have to be 0 because you could 0 them out. Good. So that in that case, maybe you have a 1 here, but 0's down here, right? In that case, what would you get? What would the rest of the entries look like? I'd argue there's like only one other element you would know. Yeah, so there has to be a 0 here, but yeah, we don't know. We don't know what these would be, right? That would depend on the matrix. And the other form we would have is just like with zeros everywhere, right? Those are those become the 3 types of reduced row echelon forms we could have. So which one looks the nicest? First one, yeah. What is the first one? Based on matrix algebra. This is the identity, good. All right, so this should be pretty interesting. This should look very interesting. So suppose we're going to show that we can do it. The all row operations can be expressed by matrix multiplication. So we showed them for the 2x2. And what we are doing is we are putting a matrix into reduced row echelon form. Let's suppose it's the identity. So at every step in our row operation, we multiply by a matrix on the left, right? Remember the ones that we did here, we were multiplying on the left. So this is our first operation. Maybe we use a different letter, maybe E. This would be our first operation. This would be our second operation. We keep going to until we end the reduced row echelon form. So this is Gaussian elimination. So just show you what's going on, right? Each E is a row operation. in Gauss-Jordan elimination. Does that make sense? So based on what we saw of the 2x2, that every row operation could be described as a matrix. We're going to show that with a 3x3, but does that make sense? Like, if you could do that, then that's what this would imply. You would not understand that? So right, this would be the first operation. So maybe you would, do some row swapping to put a 1 in the first position, and then this would be your second operation. Maybe you want to delete some of the entries in the first column, and then the last operation, you finish deleting some entry and you get the identity back. Yes, no? Okay. So what does that imply if you can do this? So we have a product of two matrices that give the identity matrix. So what does that mean? Not symmetric. Inverse, correct. And that's very nice, right? That's the definition of an inverse. If you can do this, if this is possible, then this En, these row operations that you're doing, is just the inverse. And that's remarkable. So all those things that you were doing back in the first or second sections, you were calculating inverses. So the claim is that if the reduced row echelon form, if the reduced row echelon form of a matrix is identity, then the matrix is non-singular. So this means has an inverse. Otherwise, it would not have an inverse. Does everyone see just kind of how kind of remarkable that is? So we had this question on like, how do you do an inverse for a 3x3 or higher, right? We had that nice formula for a 2x2, which didn't require any of this. But now we're saying that, well, all it really amounts to is doing row operations. All right. So let's think about what these row operations look like in higher dimensions. All right. Oh, so I think we can do it. So let's do row 1 swap row 2. Oh, didn't do anything there. Let's do row 1 swap row 2. So first of all, can you tell me what the last row will be? what would a GHI be that does row one swap row two? Good. And why is because, well, GHI doesn't show up when you do matrix multiplication in these rows, right? GHI only shows up in the last row. And the only way you can get row three back is that if these two are zero, because they're contributions to row one and row two, and if I is equal to one, good. All right, so now where something differs is, let's think about the second row. What would the second row be? So you can just multiply it out. So what would the second row be? It would be D row one plus E row two plus F row three. So 1, 0, 0, yeah. And then what's the first row? That one is 0, 1, 0, yeah. So, and that's it. So doing, this is the row operation that does, see 0 row 1 plus 1 row 2 plus 0 row 3. This one is 1 row 1, 0 row 2, 0 row 3. 0 row 1, 0 row 2, 1 row 3. Sure, yeah. So first of all, we could just do this all out by just doing this multiplication. So let's do the first row explicitly. So what is the first row? Is this and this. So it's A row 1 plus B row 2 plus C row 3. Now, if I want to make it into the row 1, row 2 swap, right, the only way I can get row 2 back is if this entry was gone and this entry was gone, and this B element is equal to 1. That's the only way I can get that row 2 back. So similarly, we can do it with this one. So D row 1 plus E row 2 plus F row 3. So we would want this to go away. We would want this to be 1, and we would want this to go away. And the last line, G row 1, H row 2, and I row 3. Since row 3 just doesn't change, we want a 1 back, 1 row 3. Good, so this is the row 1, row 2 swap. All right, can we figure out maybe what row 2, row 3 swap would be? So what will be the first row in a row 2, row 3? Yeah, so the first row doesn't change. So if you want to think about it, it should look like the identity matrix, right? Since it doesn't change. Now, what's the row? Yeah, the row 2 swap, I want to put a row 3 in the third position. And then in the last row, I want to put a row 2 in that position. So that gives row 1, row 3, and row 2. So are we kind of seeing the pattern here? So let's do row 1, row 3. That's the last type of swap we can do, right? Will be row 1, row 3 swap. No, yeah, it's fine. It's first time seeing it, so can't really think fast yet. Yeah, that'd be 0, 0, 1. So this gives the row 3. Then what's the second? Yeah, it's 0, 1, 0. And it should look like identity, right? This is what the identity would look like if it, right, since nothing changes. And then I have 1, 0, 0, because I want the 1 and the 1. Okay, so that's half the battle, or a third of the battle. So we can express row swaps in 3x3s. Now, does this make sense in 4x4s and 5x5s and n by n's? Well, sure, right? Nothing special about 3x3s that make this reasoning true. So you do the similar idea for higher dimensions. We'll discuss that at the end. All right, so let's go down the list and do 2x2s or type 2s. All right, so with A, B, C, D, E, F, G, H, I, row 1, row 2, row 3. And let's start with alpha row 1. All right. Can someone tell me what it might be? So I want to multiply row 1 by alpha, but keep everything else the same. Yeah, alpha 0, 0, right? I don't want any contributions of row 2 and row 3, right? So that's why I get 0. I want an alpha contribution of row 1. And right, and since everything else is the same, it should look like identity. So this part looks like identity, just as this doesn't change. So, and that is true. Exactly, yeah, we're just changing the ones, just like we did the 2x2s. So yeah, so this is the alpha, this is the row 1 to alpha row 1. So can we do the alpha row to row 2? So yeah, so which one are we changing? Good, yeah, so the top and the bottom look like identity because those are not changing. And then the middle is the only thing that's changing in row 2, and we put an alpha in row 2 in the second position because we want alpha times row 2. Okay, and then let's do the last one. Row 3, alpha row 3. So where does the alpha go in this case? So rows 1 and 2 are not changing, so that gets identity. The only thing that's changing is the third row. And how is it changing? By alpha times the third row. All right. So these are our type 2 row operations. So it's the identity matrix with an alpha on one of the diagonal entries. All right, any questions on that one? Okay, so let's do type 3. So type 3 is the hardest one, but I think we've built up to it well enough. So just before we do this one, is anyone just totally lost of what's going on and kind of see what we're doing? All right, great. Okay, so let's say I want to do a common row operation you would do, like the first thing you would do in a row operation or Gaussian elimination. You change row 2 to add alpha row 1. So I think a good place to start is to look exactly at the rows that are not changing. So look at the rows that are not changing. What does that tell you about your left matrix? So based on these entries here, right, the first row must be 1, 0, 0, which should look like identity, and 0, 0, 1 for the third, because it looks like identity. So when thinking about these types of matrices, that's a good place to start, is just let's focus on what's not changing. And then we can spend our effort on the only row that is changing. Good, yeah, it is alpha 1, 0, right? How many alphas, how many row 1s are contributing? It's alpha. Only one row 2, and then no row 3s. And that's it. And again, if you forget this, you can do this out and do the matrix multiplication out with a row 1, row 2, row 3 like this. And there's your type 3. Can 0, 0, 1 be the first row? Yeah, let's think about it. In type 3 operation, can someone give an explanation of why there has to be a diagonal full of 1s in a type 3 operation? So actually, no, not for a type 3 operation. What's the only scenario where you have a 0, 0, 1 as the first row? What operation would that imply? That's one we did earlier, right? That's the type 1, yeah. Yeah, you can only have a 0, 0, 1 if you're swapping. So that's another kind of indicator of what type you're looking at. It's the diagonal entries. So if there's a 0 in the diagonal somewhere, then it's a type 1. If there is something that's not 1 in the diagonal, then it has to be a type 2. And if they're all 1s in the diagonal, it has to be a type 3. And if there's some number that's not, or, well, yeah, let's say with all 1s in the diagonal as a type 1. All right, so let's just do another one. What's another common one? How about like when we do Gauss-Jordan elimination, we might do this upward elimination. So like row 1 to row 1 plus alpha row 3. We pivot off the third row. So what do you think this one would be? Is that P a 0? Yeah. 1, 0, alpha. And then everything else is the same, right? Yep, this is row 1 plus alpha row 3. All right. Cool. So everyone okay with that? The type operations? All right, so just for the challenge, let's do a 4x4. And let's do row 3 plus it's an actual number plus 7 row 1. All right. What do you think the first row would be? Wow, that was quick. Good. Yeah, so since row 1, row 2, and row 4 are not changing, those entries should look like the identity matrix. And now for the third row, the row that is changing, there needs to be a 1 in row 3, and there's no row 4, there's no row 2, and a 7 in row 1. So maybe it'd be even easier to write it as 7 row 1 plus maybe like row 3. Good, yeah, so you can do these for every case, even n by n. It's tricky to kind of come up with a formula for that, but you can do it. So this is very remarkable because of this inverse problem. So let's actually find an inverse. What was your question? Just curious. Okay, that's fine. Okay, let's find the inverse of this if it exists. All right, so when you replace it, yeah, but that's the kind of the beauty of this is that you could usually you'll have a 4x4 to work with, right? But you can just truncate it to this column of rows, and it'll make it easier to kind of understand, you know, what the entry should be, right? And then you can, once you know, the idea is once you know this, then it's fine, right? Then you can just do the multiplication 4x4, as you know, hard as that might be. You know, it's just there's actually not much to do, and you know the row operation anyway. Right, so you tell me, what would the first row operation be you do in this for this problem? So the idea is we want to put this into reduced row echelon form. If it's identity, then we can actually calculate the inverse. Yeah, row 2 to row 1 minus row 2. Yeah, so why don't we do it first and then construct the inverse. So -1, -1. Oh wait, I don't want these numbers, I'm sorry. Let's try that. One. This should be it. Okay. All right, so sorry, I just changed the numbers. So I changed that 3 into a 1. All right, so okay, that's the first operation. What would your second operation be? Sure, we can swap row 2, row 3. You would know how to do without doing it, right? But yeah, we can do that. All right. Now what? So we swap row 2 and row 3, and then what do you do next? We want to get rid of this entry, right? Yeah, row 2 plus row 3. So row 3, 2. Oh, we could do it type 2. I think just getting rid of this would be better though. Row 3 plus row 2. Okay, now what? We're doing reduced row echelon form. Yep, half row 3. This puts it into Gauss, puts into row echelon. Okay. So now we're limiting upwards, right, for reduced row echelon. So now what? Yep, row 2 minus row 3, and then what's another one you can do simultaneously? Well, not row 3. I can also do, I can get rid of this entry too, right? Row 1 and then row 1 minus row 3. Just to expedite it a bit. And the last step, row 1 to row 1 minus 2 row 2. All right. So what does this identity matrix at the end tell us? So I have the sequence of row operations, and at the end we get the identity matrix. So what does that mean? It has an inverse. Yep. So all these row operations I'll denote by e's, which I haven't even defined yet, but these are called elementary matrices, which I'll define, but we don't really need to define right now. So the idea is that at each step, we multiplied by matrices that were row operations. And we got the identity back. So what is the inverse of A? It's all that stuff, right? It's E7, E6, 5, etc. All right, so why don't we not multiply all that out, but let's at least list out these operations. All right, so let's do, what is E1? what's the row 2 minus row 1 matrix? So again, this is a type 3, and the changing row is row 2. So that means that the first row stays the same, and the last row stays the same. And now, what is the second row going to be? -1, 1, 0. Okay, let's take E2. So this is our row swap matrix. So we're swapping row 2 and row 3. So row 1 is not changing. And then what happens in rows 2 and 3? Zero, zero, one, and 0, 1, 0. Okay. Then we did a row 3 to row 3 plus row 2. So the first 2 rows are not changing. The second one in E1. Oh, it is -1 here, because the -1 is attached to the R1, not to R2. Yeah, it's a little misleading with the order, but it's actually 0, 1, 1, right? Because it's not plus 2 row 2, it's just plus row 2. Does that make sense? How about E4? This is a good question because you get all the types in there. So thank you to whoever suggested the row swap. Okay, how about E4? So we're dividing row 3 by 2. So yeah, so I get a 1/2 in the last one. So E5. So this was row 2 to row 2 minus row 3. So yeah, what's in the second row for E5? 0, 1, -1 in the second row. So there's a minus row 3 there. And then the first row is 1, 0, 0. D6 is, yep, 1, 0, -. And finally, let's do E7. So row 2 is not changing. So let's E7. So I want a 1, right? I want a 1 here. But this gets the -2, and then a 0. So I still want a row 1 contribution. All right, cool. So the claim is if you multiply all these out in the correct order, then you'll get the inverse. Be practical. We'll find another way to find the inverse a lot easier, but it will kind of be the same idea as what we're doing here. But we'll probably do that next time. So any questions on this? So everyone see the power of describing row operations as matrices? I think mainly for right now, the power is in inverses. If you can express, if the reduced row echelon form of a matrix has identity, then it has an inverse. And that's because every single operation is a matrix. That implies you can find the inverse. While tedious, we'll find a better way of doing it. It implies inverse exists. And we'll even see how the determinant plays a role later. Okay. So questions on this? Okay, so to finish off class, we'll talk about the inverses of, well, let me just first define elementary operation. Elementary matrix are matrices that that behave like row operations. Yeah, that'll be the eventual claim. We'll need to prove that if the reduced row echelon form is not identity, then it will turn out and not have an inverse. Right now, it's not obvious, but the other way is true, just based on like this fact that since row operations can be described as matrices, this automatically says if reduced row echelon form is identity, then it has an inverse. But the converse isn't necessarily true yet, but it will be. So in those other cases, like these cases, it'll turn out that it won't have an inverse. So let's think about inverses of elementary matrices. So is it not right to talk about inverses of elementary matrices if we haven't talked about inverses yet? Not really, because I think it's very kind of clear how to describe inverses of elementary matrices. So let's think about inverses based on how we have been talking about them as like undoing the undoing matrix. So in big quotes, it's not a real thing. So here's just a kind of, let's do by 2 by 2s. So this is the row swap matrix, right? We can do 3 by 3s. So this is the row swap matrix. This is the row 1, row 2 swap matrix. How do you know it has an inverse? Immediately you should know this has an inverse. So remember, think of this as a function. This is a function. It's actually not in reduced row echelon form because of those ones. But I'm not thinking of after swap yet. But yeah, so with not even thinking about reduced row echelon form, and think about what you just said, after you swap, then it's identity. How do you, so if you row swap row 1, row 2, and you said, uh-oh, I didn't want to do that, so let me undo that. How do you undo a row swap? That question makes sense? If you row swap, how do you undo that? How do you go back to where you started? Swap back, yeah. And I don't need to calculate that because we should know that it's intuitively, right? Doing 2 swaps does nothing, as long as it's the same swap, of course. You can't swap 2 different things and get the same thing back. So let's think about that as well. If when thinking about these matrices as actions, let's think about how to undo these actions. Okay, here's another function. Okay, I multiplied alpha to row 2, and I said, shoot, I do not want to do that. How do you undo multiplying alpha by row 2? Or multiplying row 2 by alpha, how do you undo that? If you multiply by something, how do you undo it? You divide, yeah. So you say, let's do it over here first. Shoot, I multiplied row 2 by alpha, and I wrote it in ink, so I can't erase it. So let me just multiply again by 1 over alpha to undo what I just did. So this is the inverse. So the inverse of a type 2 is you divide. Okay, and then lastly, let's do a type 3. So I added alpha times row 2, sorry, alpha times row 1 to row 2, but I don't want to do that. I want to, let me just write it out. Actually, let's do a different one. First of all, you tell me, what operation is this? So what row operation did I just write? Good, yeah, so it's row 3 to alpha row 1 plus row 3. So how do you undo that? So I've added alpha row 1 to row 3, but how do you undo that? Subtract it. Yeah, these are just normal things, right? So this is the inverse, right? If you add alpha row 1, and to undo that, you subtract alpha row 1. If you multiply by alpha, to undo that, you divide by alpha. If you row swap, to undo that, you just do it again. Right, so any questions on these inverses? So right now, already, you can see that every single elementary matrix are non-singular. So this is something that will play a role later. The fact that they're non-singular is pretty important. But so yeah, but any questions on that for now? So finding the inverses of these elementary matrices are right now quite easy. You just think about what would the matrix be to undo that operation. Okay. All right, so to finish off, we just have a few minutes, but I want to talk about other types, column operations. So first of all, when we talked about row operations, we used this idea, so that we can talk about a matrix as a column of rows. Now, what we couldn't do, however, we could not do this. And can someone tell me why? Why can't we talk about it like that? So can you talk about a matrix as a row of columns? Is that okay? As like this? Someone say why that's not good. What's wrong with this? The dimensions are incompatible. Yep. This is a 2 by 2, but if I express this this way, this is a 1 by 2. So we can't do that. So does that mean that you can never talk about column operations? No, but let me ask you this: how could you incorporate this vector? Well, where would that need to be to make that? So if it was 2 by 1, that would be this one, right? So I just can't make that 2 by 1 because those are columns, right? Yes, if the first matrix, if this one was 2 by 1. So this is okay. That's okay. So it turns out that column operations are thought about as multiplying on the right. So row operations, so maybe the ABCD was a row operation that changed row 1 and row 2. However, with column operations, they're the same operations as before, and we don't have enough time to really go through all of them. But let's just maybe let's do a row swap. So let's do same reasoning as we did before. And I want to make this into C1. So what does this operation give you? It gives you C1x plus C2z and C1y plus C2w. Okay, so what does x, y, z, w need to be to give you C2, C1? Yeah, it's the one that we had before. So this is, so if you multiply A, B, C, D times 0, 1, 1, 0, you don't get a row swap, you get a column swap. So multiplying on the right, multiplying elementary matrices on the right, so on the left, are row ops. On the right are column ops. So next time maybe I'll go through maybe a couple more of the column operations just so you can see. But if you know the row ops, you're fine. Sometimes the column operations might come into play, but I would encourage you to go through, at least for the 2 by 2s, to kind of show for yourself why go through type 2 and type 3, the matrices will look the same. All right, so I'll stop recording.